Okay, so now in the setup, double click here and this will open the Fluent dialog box or Fluent launcher. And from here, click on the server processor. So let's say the mesh number of nodes are around 40K. So I would be going with the one processor, maybe with the two processors. And click on the start. So it's starting the Fluent. Okay, so you can check the scaling. So scaling should be like the how much height we have provided. In Z direction we have the 0.0257 and in the X and Y direction they should be almost same. So it's a 0.007. So 0.007 it means that's is equal to 0.007 046 into 2. It's a 0.014. It's a 0.01414 diameter, and for the orifice diameter is a 0.0002. So diameter of the tank is 0.01414. Now it's because of the approximation. It's a 0.014092. This is okay. The next thing is a checking of the mesh. So the important thing here is the minimum volume should not be negative quantity or zero quantity. And then click on report quality. The orthogonal quality is minimum orthogonal quality is a 0.4. It should not be less than 0.01. And the aspect ratio is around 10. It's okay. For VF model, the value should be lower. So maybe lower value than the 10 may be much better. But with a lower value and high number of nodes, you have to make the very, very, very fine mesh. And that is not feasible for this demonstration purpose. So that's why I kept the mesh number of nodes very low, and it will make the cell size larger. But I just kept the sizes so that we can have the square elements. With the square elements, the aspect ratio will be lower. And now display mesh. You can put the display with the edges. Okay, I think that the boundary condition are not set properly. So if you put the name selection in the proper way, the names type can be decided very, very easily. So if you go to boundary conditions without setting anything at all right now, so in the bottom side is a wall, okay. Orifice should be the pressure outlet. And don't define any condition at all. We will keep the default settings. And top surface is also pressure outlet, which is going to be will be acting as a free surface, because air will be going inside from this surface inside this volume. So you can see. I will check this thing later on. So now if you display the mesh, you can see the color change. So red color is for the pressure outlet. Same is the case on the bottom side. And the wall has a gray color. So we have the two walls, the circular wall and this bottom wall. So the circular wall, I call this wall as the outer one. You can see. Okay, you can also go to colors, and from here you can color by ID. So reset colors and display. So now you can have the different color for the different surfaces. Okay, now close this one. And from models, I'm going to define the multi-phase. And before that, I want to define the material properties and click on create edit. So I want to add the new material, that is the water. And for that, click on Fluent database. And then scroll down and select the water liquid. And click on the copy. So you can see that we have the now new material, which is the water liquid. And now you can go to models and double click on the multi-phase. And choose the volume of fluid. Number of phases are the 2. Okay, so as soon as you click and apply, you will see this phases part will be activated. So click and apply. And now we have the phases and as well as the phase interaction. Also we have the population balance model, which we don't use right now, as for some other applications. And in the primary phase, you can see we have the air. So I discussed in the previous video, the lighter fluid will always be selected as the primary phase, and the heavier fluid will be taken as the secondary phase. And second logic is that the any fluid which will remain in the domain will be the primary phase, because air will be filling there when the water is drained out from the domain. And so the secondary phase will be no more when the simulation will be ending. So primary phase will be there. So that's why the primary phase is air and secondary phase is the water. And now close this panel, and in the viscous, double click here. And here I will be choosing the K epsilon, realizable, and scalar wall function. So we don't choose a standard function because this is not a very good model with realizable. It has some constraints on the reliability of the model. So the best option in the K epsilon is realizable. And why we are choosing this model? Because the K epsilon is better in these situations. And the K omega SST is used when we have the especially the boundary separation, or when the flow is dominated by the wall. But right now the flow is free shear flow, means that there's no much effect of the wall on the flow. That's why we're using the K epsilon model. And click on OK. Alright, so now go to boundary conditions and just check the bottom is the wall. Orifice, if you take a look here, you'll see the standard boundary conditions are there. Gauge pressure is 0 because operating pressure I will discuss here is 101325. But if you take a look on the phase 1, so phase 1 there's no condition, but it depends on the phase 2. So we don't give the conditions for the phase 1 directly, but we do provide the conditions for the phase 2. So if the phase 2 is something, the phase 1 would be equal to the 1 minus that value. So now if the phase 2 is let's say the backflow of the phase 2 is 0, it means that now from this boundary, let's say, or orifice, because both are the pressure outlets, so from this boundary, if there is some backflow, some reverse flow, so there will be no water flowing inward the domain into the domain, but the first phase, which is the air, will be flowing there. That's why when I define the pressure outlet on the top condition, what will happen is that because we don't have any water there, and that will be in the suction mode now. So with the backflow, that is the air, will be coming into the model, and that's why I defined the pressure outlet there. So now you can see that with the phase 2 as a 0 and phase 1 would be equal to the 1 when there will be reverse flow. So apply, and same is the case for the top, which is basically over here. So top is basically is the important boundary here, because here air will be going inside the domain, but from the orifice all will be is going out is the water. There will be no air going inside the air from this boundary. Maybe at some last stages of the simulation, maybe some air may go inside from there, but I don't think so. And this outer is the wall condition, and so is this bottom condition, which is in the pink color, which is over here. Okay, so we have defined all the boundary conditions, and we understood all their requirements and what is happening there in the boundary conditions. And now next thing would be so I will leave the mesh interfaces, I will leave the dynamic mesh, no reference values, no reference frames, and no name expressions. Just check the methods that it should be the pressure velocity coupling should be simple, and pressure automatically is changed to presto when we selected the VF model. Momentum is second or upwind, and the volume fraction is calculated based on the geo reconstruct. This is also a default scheme for the VF model, and turbulence quantities, they are computed with the help of the first order upwind scheme. I will just keep as it is, and transient formulation is first order implicit. Maybe you can try with the second order implicit. You can see yourself. So I will not do that thing in this workshop. Maybe you can try that thing as well. Okay, now in the controls, in the report definition, I will not be putting anything at all, but in the monitors, I will be changing the residual monitor criteria from 0.001 to the 0.0001 for all the variables. So add extra 0 here, and then click on the OK. Okay, now I will initialize the simulation from the 0 values for the X, Y, Z and the gauge pressure. And before that, okay, you can change the phase 2 volume fraction to the 1. So all will be the water inside the whole domain. So phase 2 is a water, that's why the volume fraction of the phase 2 will be 1. It means the volume fraction of the air will be equal to 0. So volume fraction will always, the sum of volume fraction will always be equal to the 1. So if the volume fraction of the water is 0.5, so the air will be 0.5 as well. 50% will be air and 50% would be the equal to the water. And before we go for the simulation, you should be checking the physics, and from here check the operating conditions. And because we didn't turn on the gravity, so just go to general panel. You can also do it from here or from here. So I will be putting the gravity, and since this is the z direction, so z direction is in the height and the gravity will be affecting the downward side. So I would be putting the value of gravity 9.81 meter per second square with a minus sign, minus 9.81. So minus sign means the gravity will be affecting in the negative z direction. And same thing also you can see over here. So if I click over here, so let's say now it's minus 9.81. Okay, just click on the operating density. You can see that we have the gravitational acceleration in the minus 9.81. Operating pressure is the 101.325. The same value is copied from here. And the only thing you have to make the change is the user input, and the operating density should be set to the fluid which has the lower density, which, so from water and the air, the lower density is of the air, which is a 1.225. So I would be putting that value here and click on OK. Okay, as far as the air properties are concerned, so air properties are because the fluid is incompressible, so that's why we have the constant density, and viscosity is always constant because this is not a temperature independent right now, so it's a constant value here. And so we defined everything here. Now I will go to run calculations, and before that I want to go to results, and from here I want to click on the iso surface. So I would be creating a center plane on the geometry so that I can display the volume fraction of the water on that plane. So that's why I will be choosing the mesh and x coordinate and compute and click on the center location. So I will be clicking on the center, and same will go for the y coordinate because I don't know that which plane will be parallel to my screen. So that's why I'm creating the plane in the x direction as well as in the y direction, but on center location. So I want to see that which plane will be useful for my animation purposes. So I have done with these two isosurfaces at the 0x, 0y, which is center location of this geometry. And so you can also display that plane here. So let's say if I don't display the outer, so you can see the x plane is over here. Okay, and the y coordinate is over here. Okay, I think I should be doing one thing. The mesh is not 100% as I needed, so I should be going back to the mesh application, and from here I think I have to do one more thing, is that the vertical lines should be selected all. So just double click here on the mesh. So from the center planes, I think we have seen this thing. So this should not be like this. Or maybe this is good because we have the more finer mesh in inward side, but let's check it. So if I click on the mesh and if I click on the display, and from here what I want is that I want to have the section plane. Okay, so click on section plane and make a section plane and see the mesh from inside. So this is like this. And if you go to section plane, you can see the whole elements, they will look like in this way. So right now the mesh is like this way. So just hide these planes and make the wireframe and click on the mesh lines over here, edge sizing, and then click on the edges. So now if I press the control key and hold it, and then I just select the mode to be the box selection, and just I go from right to left, I can select these edges. Sorry. So select the edges first and then click apply. So just keep the control key on, otherwise we will be losing the edges. So now 12 edges are selected here, and simply click on the generate. And again go to the section plane and make it like this. So now you can see the number of nodes they will be like this. Okay, so there's some issue in the mesh, so I want to check it. So edge sizing here is the soft, so make it hard. And edge sizing here is also soft, so make it hard as well. And again soft, so make it hard. And now generate the mesh. And now again check the section plane. So now this looks good. So the only issue I am facing here is the way the mesh should be done here. So what I should be doing is that I would be going to my mesh. This mesh is okay. The second mesh is like this. This is also okay. So let's just check. So the more nodes distribution should be here. So what I should be doing is that I would be putting the number of cells maybe 6. Okay. And with the biasing, I would be putting the biasing here, and bias factor, let's say, is the 5. And I will be reversing the biasing over on these two edges because they are going in the other direction. So put the biasing reverse on these two edges and press the control key, just hold it and apply and click on generate. So now I think you can make it biasing to the 2.5 and again generate, so that we should not be having the too much mesh towards the center plane. It should be smoothly going outside. So now this is okay. The next thing would be the mesh biasing over here. So I will be putting the mesh biasing here with the biasing factor to be 5. And reverse bias I will be setting on these two edges because they have the more size towards the outside. And then apply and click on generate. So this seems much finer. So maybe you can try with the bias factor of 6 and again generate. Okay, so this is not being copied on the top edges. This is not being copied on the top edges. So if I delete this method from here, okay, and go to mesh and click on method, select all the geometry, apply and select the sweep method again and generate. So it is working in a different way. You can see if you select this before and then after, this will be working in a different way. So now the source and target selection, let's say I make it as the manual source and target. So the source is this one and the target is this one. Okay, now click on generate and let's see what happens. Now the mesh looks okay. So now you see that if you put the sweep method first, the effect will be different. If you put the sweep method later on, the effect will be different. So, and also if you select these faces manually, you can see that how this is going to work. And also make all the free mesh types should be all the chord elements. And now check the mesh from the center plane, from the section plane. And now you can see the mesh looks very good here. And now you can close the mesh app, and before that you can update the mesh so that we can transfer this new mesh into the Fluent. And simply close this app and now click on this refresh input data of mesh setup solution over here. Click on yes, that the upstream mesh has been changed. and this will be reading the mesh back into the Fluent. Number of cells are now 20,000. Okay, now you can see the mesh from inside will look like in this way. That's okay. Okay, one more thing I should be making, which I not be doing right now, is that you should be making also more concentration towards this wall as well. So this might be in your assignment. So this is going to be assignment or project for this whole course. So you should be making the more concentration towards the wall as well. So here should be mesh fine and here mesh should be fine. And you can just keep the coarse mesh in the middle. Okay, so we have set these conditions, and now I'm going to make the initialization with the volume fraction equal to the 1. Okay, then in the calculation activities, I will be selecting the solution animation. This is very important because otherwise you will not be seeing the any flow development here. The tank will not be, you can solve the problem. But what I want is that I want to make the animation. So for animation, you have to set the animation from here, and click on the new object and the contours. And this is going to be the contours of the phases, and volume fraction, yes, volume fraction, second phase, which is the water, and uncheck the global range, auto range, clip to range, and put the ranges manually 0 to 1. And that is going to be on the first try on the x coordinate, and then on the x coordinate, then the y coordinate. So, and also from the views, uncheck the option for the lighting. So this will be more brighter here. Okay, now from the animation definition, so let's say I put an animation name is animation, and it's a water phase. Okay. So then from the animation view, click on the manage views. And now I want to see that which view is going to be the useful for me. So I will check with the back. No, it's not. You can also zoom the geometry. No, it's not there. Bottom is not also there. Front. No. Left. But it's not a vertical, but this is a like laying on the one side. This is not required here. The right one also not good, and top one also not good. So I will now try with the second plane, which is the y coordinate. So uncheck the x coordinate and play on the display on the y coordinate. So this is what I want. So it should be z direction positive in the upper direction, and this is what I need here. And now you can close, and you can select the top view from here. And so again, once again you can edit the object. So we have the volume fraction of water to be from 0 to 1. So basically we will be observing the water phase when it is draining from here. So initially this is full of the water, and then once it is drained out, you will see the blue color appearing here for the air. And in the color map, I will be selecting the band-aid, and the number of layers may be 20. And if you just make the 2, so you will only be seeing the either water or only the air. So no mixture of the two things. And save display, close, and OK here. Now in the run calculation, I will be putting the adaptive time stepping, and it's a multi-phase specific. I will be putting the incremental time steps. So you can put the number of time steps, although we calculated it to be around 2000 for the time step of 0.0002, but because we are using the adaptive, so we don't know when this will be ending. So maybe you can go with 1000 or maybe 10,000. So we will stop manually when you will see that flow of water is no more there. It's very, very low on the bottom. And in the settings, the maximum time step I will be limiting is to the 0.01. And the minimum step time change factor is a 0.8. So when the solution is converging in the less iterations, so it will reduce the time. It will increase time step, and when the solution lot converging in the 20 iterations, that is a per time step, it will decrease time step by the factor. So now maybe 0.01 will convert into the 0.008. Okay, so save it. And also extrapolate variable. This will help you to accelerate the solution, but if not required, maybe you can just keep it as it is. And now click on the calculate. So you can see that now we have the blue color shows the air, and red color is the water, and in between these colors are the mixture of the air and the water. So it will take some time, and once solution will be converged, I will come back here. Okay, so I'm just stopping solution to check some parameters. So click on the stop and add the time step. Okay, so you can see that we have the option here, report simulation status. So this is given here in the new versions. So you can see that right now the time step size is selected by because initially we set the time step to be -5, but because solution was converging properly, so the time step right now is a 0.0039, and total flow time is a 0.2, and as you remember that the time which it will take to empty tank is the 4.3828. So right now it's a 0.2 seconds. Total time steps are 59, total iterations are 1180. So if I divide this total time steps by the iterations, 1180 divided by 59, so 20 iterations for the every time step. And also the minimum time step it used is a -5, 10 power -5. Now it is 0.00395. So it is basically is setting itself automatically. Now we can continue with the calculation. So click on calculate. Okay, so I stopped solution here, and also from the residuals I changed the conditions for the convergence, because solution was converging at the very faster pace and it was only taking the few iterations like the 4 maybe 5. So what I'm doing here is that I am just making it relative, and the relative criteria I'm going to give is that it should be being converging in the like a 0.05. So error from the last step and the new step should be not more than 0.05. So now click on OK, and also click on the report simulation status, and it should be turned on. So you can see it on the screen. Okay, so you can see now that it is converging in this way. And you can also see these all things over here. So right now time step size is 0.001477. Now it's a 78, so it's increasing at the some pace, and right now the flow time is a 0.7918. So you can also see that it is now almost 1/4 is empty. So is the time also is 1/4 is already done here. Okay, you can observe that the time step size is being increased, which is now 0.00156 and 565. So it's changing very slowly, but it's changing. So depending on the convergence criteria, it is changing. And right now total flow time is 1.02169. Total time steps are the 586. Total iterations are 8169. So you can observe here the time step is being changed here. 572. 572 is still there. Now the 573. 574. So it's changing. So I will come back after like maybe flow time after 2 seconds. As you can see that the total time right now is 3.849 seconds, and the flow has been fully drained almost, but there's a little flow here, and if I remember correctly, the time it will take is a 4.38 seconds. So now you can understand that it almost took maybe 3 seconds to empty a majority of the tank, the water inside the tank. The last flow, because it has a now very low pressure, low level, so it will take more time to drain as compared to the 80% of the flow. But anyhow, I will leave this simulation running and until I reach the total time of the 4.3 seconds. Okay, now you can see that the flow is almost is no more there, and the time it is taking is almost is 4.3 seconds, and we were targeting about 4.38. So now it's time to stop. So I will click on the stop at the end of time step, and if not, then you can press the control key and control C. So control C, this should stop the simulation. Okay, so total time is 4.34 seconds, and the one more important thing is that why I used the adaptive time step, because we had no idea that which time step would be suitable for this simulation. So maybe we can choose a 0.01, 0.005, 0.0001, and all situations, maybe some time steps may give you converged solution, and the very lowest time steps may require the many time steps. It may take the more CPU time, the clock time, as compared to the actual time of the simulation. So that's why with the adaptive time stepping, you get the idea that the which time step would be suitable. So right now, as you can see, so right now is a 0.0013, and but we have decided about the 0.0002. So it means that the 0.0001 or 0.005 between that time step is a good enough. So what you should be doing? You should be doing the simulation with a fixed time step and get the idea of time step from the adaptive time stepping. So all the time step all the time steps should be on the same time step size. So I would be putting maybe 0.0005, and I may run this case for the maybe more than like 4,000 time steps, maybe enough. So for example, if I divide this time 4.3828 divided by the 0.0005, the time step it will require will be 8,765. So maybe I can run this case, and it will take maybe total one day on this computer with this much mesh. But that would give you the constant time step, and that's good for the animation and the simulation purposes. So anyhow, we can now close here, and the first thing we should be doing is to save the project. And the second thing would be to make the animation. And now you can see that although majority of the flow, 90% flow has been drained out maybe in the first 3 seconds, maybe or less than that time, the remaining flow took more time here. So now it is saving the solution. Now you have to, so if you remember that we made the simulation animation from here. Now to make the animation movie, you have to click on the playback, and you will get all the time steps and frames. So for every time step, we have the one frame. So since we have the 2301 time steps, so we have the 2301 time frames. So you can just change the record format to the video file, and then click on the write. And for this much time steps or the frame, it will take time, and maybe the Fluent will freeze for some time. Maybe you can see not responding, but don't panic. Just let this Fluent to finish the animation generation. So just wait for it. And since we have the 2300 time steps, so it is writing the frame for each and every iteration, each and every time step. That is the in terms of animation, this is a frame. So almost it has written the 1135 frames. So I will just wait for this to finish. And if you move the mouse and the Fluent window too many times, this may close down the Fluent, and it may stop the generation of the animation. And in the worst case scenario, this may also lose the data from the Fluent. So don't panic and don't move your windows, the Fluent and anything. Don't make any changes over there. Don't cross the window of the Fluent. So just wait for this simulation, this animation to be finished. So right now it's So it will take some time, maybe few more minutes. Now, as you can see that the animation has been generated and it is in the working directory. So I will directly go there. It is in the D drive and tank empty VF files, DP0, FF, Fluent, and these are all the files, all the frames written here. So scroll down, you will find the video file, animation file here. So the name I have put on the file was the, if you remember, it's the animation water phase. And if you double click here, this will play and you can see how the flow is developing here. And you can also change the levels. So we put the 20 levels, you can put the 11 or maybe 2 or maybe 30 or maximum 100 you can put. And also you can, right now it's a band-aid, you can also make it smooth. So now it's slowed down in the bottom side. You can see the flow is going from the hole on the bottom, and that's why this is happening here. And now it is like the flow is being drained from the sides, and it's a very nice simulation which you can see here. Now it's taking more time to drain this flow because this flow is very, very low in the level, and this is very much physical. You can observe in any tank, if you fill the water and if you observe, you will see the same thing over there as well. So now we are finished with the animation part and with the Fluent part as well. And we have set up the everything from scratch. We made the geometry, we have made the calculation analytically, we made the meshing, setting of the problem, we discussed everything in the detail. And now I hope that you can understand, and now you can use this technique on the similar problems. So for example, if I take you to the problem which is very well-known problem on the VF, that is the drainage of the tank. So there's a flush tank. I just show you shortly right now. So for example, in this video, you can see this is the, now there are the two domains. So one is with the tank with the full, and second is on the bottom side. So you can also make the same thing. You can make the orifice, and then you can also put the another tank on the bottom side, and you can make this as a free surface, also this one as a free surface. And so same simulation you can also make over there as well. So you can see that how it is going to establish the flow. So here we have some flow here, and now it's discharging from there. So it is the air and water is going inside like this. Okay, so thank you for watching this workshop, and I hope this will help you to understand the multi-phase modeling with the VF in the Fluent.